Cool. So hello everyone. My name is George Xu. I'm a HCI researcher from Dartmouth College, where I just finished my PhD in computer science. Today I want to present our work, SkipWriter, LLM-Powered Abbreviated writing on tablets. This work was completed during my research internships at Google, and is in collaboration with my mentor Shanqing and Shuming, as well as Suba from Google Research and McQueen from UCSD. Today, mobile text input has been a very important component of our daily life. One of the directions in text input research is to use predictive technologies for better input experience, and the recent rise of large language models offers transformative opportunities in this domain. Conventional predictive interfaces like word-for-word suggestion on today's smartphones is typically powered by n-gram language model. Transformer-based large language models have enabled phrase level for word suggestion, like the Smart Compose in Gmail, to help users save more input efforts. Phrase abbreviations is another domain where LLM can make huge impact. Abbreviating phrases is a naturally developed behavior in SMS, where a common phrase, as far as I know, is written as AFAIK. However, the applications are limited to common phrases due to the poor readability. Previous research has investigated the feasibility of expanding initial-only phrase abbreviations using LLM and observed a 70% success rate for dialogue phrases. Our goal in this work is to create a generic text input method where text can be abbreviated in chunks to minimize human input efforts. We want to achieve that by harnessing a large language model decoder specifically developed for this task. To achieve this goal, we made choices in various input modalities and abbreviation forms. And also we addressed challenges in decoder training and interface design. But before diving into these perspectives, I want to first show you a quick demo. This is a video showing the user writing "Thank you for your support" using SkipWriter. In many cases like this one, the user can abbreviate each word by only writing the initial letter, and the LLM decoder can successfully predict the full phrase. As a proof of concept exploration, we chose handwriting as our input modality because it has prolonged stress on the hand and wrist, making it very exhausting for users. In other words, handwriting can significantly benefit from reduced physical efforts. Also, in the cases when the initial abbreviation fails to be disambiguated, the user needs to modify or complete the abbreviation. The flexibility of pen-based interaction enables random access to the sequence of the word prefixes, so we don't need an insertion cursor to specify the concerned word. Among many existing abbreviation forms, we adopted variable-length, prefix-based abbreviation proposed by Li, Quinn, and Zhai. It can be taken as a natural extension of the SMS language. This abbreviation form has the flexibility in the abbreviation length, so all prefixes of word are legit abbreviations. So, for example, the word today can be abbreviated as the initial letter T, or TO, TOD, TODA, or the full spelling TODAY. This flexibility gives us two advantages. First, it has very high ceiling of character savings, so as each word abbreviation can be as short as one single character. This is very helpful to unleash the power of large language model. Second, each word can be gradually completed if the disambiguation fails. And the acceptance of the full format guarantees the successful entry of the intended text. More importantly, the way to complete and extend an abbreviation is very easy and straightforward. Users can progressively add more characters at any time, which can help maximize the number of characters that are skipped. Now, we will talk about the technical details. We adopted a recognize, then decode approach to avoid the costly data collection from human subjects. In details, we use an in-production handwriting recognizer to transform handwritten strokes into digital format. followed by a checkpoint of parm2, which is fine-tuned for this task to expand the abbreviation. To do fine-tuning, we need to first construct a training dataset. We chose the data synthesis approach to arbitrarily generate abbreviations for millions of phrases. For example, if the target phrases have a way of, the generated abbreviation can be HA, A, WA, O, or any other combination of word prefixes. We generated millions of phrases from 4 public datasets, including academic papers, movie reviews, news, and Wikipedia articles. When decoding an abbreviation, so the preceding text is also made available to the large language model to improve the decoding. Let's see an example here. So in this case, the user has already finished the text. LLMs may offer transformative opportunities for text input, especially for physically demanding. And the user is going to write an abbreviation for the next phrase, modalities like handwriting. The input signal, which is the user's handwritten abbreviation, will be transformed by the recognizer into the digital format MODLH, and combined with the preceding text for LLM to predict the full version of the intended phrase. Besides building a LLM decoder, we also face the challenge to design an interface that can encourage users to try and employ shorter and more efficient abbreviations. As you can see in the previous demo, there's a segmented rule on the interface. It has several unique benefits. First, it enables easy editing to the abbreviation by serving as an ambient reminder for users to leave space between 2 words for future completion. Therefore, it reduces the overhead of post hoc completion and encourages users to try more aggressive abbreviations and therefore maximize the modal savings. The second benefit is that it serves as low-cost word delimiters. Otherwise, as the handwriting recognizer is not trained on such kind of input, a mixture of word prefixes, it can easily misrecognize the abbreviation without robust denotation of word delimiters. This rule is also used for inline visualization of the top candidate to minimize users' visual attention switch between the handwriting area and the candidate bar. Before heading to the evaluation, let's see a longer demo of SkipWriter. This is the first sentence of the paper's abstract. You can see the user can easily add more characters to extend the prefix and obtain the target word. We evaluated our prototype with 10 participants, where they were asked to transcribe given sentences. We also include conventional handwriting on Gboard as a baseline condition in the study. We observed slightly faster speed and lower word error rate, though the differences are neither significant. However, we observed a significant 60% reduction in handwriting efforts. It is measured by a metric named traversal distance per character, meaning that the average distance the user's stylus tip needs to traverse on the screen to commit 1 character in the final text. We are also interested in the efficiency of the abbreviations users adopted in the study. We want to know whether users are willing to try shorter abbreviations on our interface and therefore fully utilize the character saving power of an LLM decoder. The simulation strategy we used is to simulate the most aggressive behaviors of abbreviating. It always starts with the initial only abbreviation, and if the target phrase is not in the candidates, only 1 more character is appended to the first wrong word in the prediction. This process is repeated until the target phrase appears. In other words, this strategy mimics a lazy user who always prefers minimum input rather than adding more characters than necessary as the safer option. Finally, we compared the observed CSR in the study with the simulated CSR. Here, CSR refers to the character saving rate, the percentage of characters skipped in the abbreviations. We can see in the study, users skipped about 66.9% characters in their abbreviations, and the simulation shows a maximum CSR of 74.8%. Here, top 1 or top 4 refers how many candidates the user is actively monitoring. In top 4 condition, the simulation ends when the target appears in the top 4 candidate, and similar for the top 1. The gap between the user CSR and the optimal CSR in the simulation is relatively small, about 10%. So meaning that users are able to utilize the LLM's potential to a substantial 90% using SkipWriter's interface. It also exceeds the model saving offered by conventional n-gram decoder by a large margin. To wrap up today's presentation, here are 2 takeaway messages. First, LLM can effectively decode phrase abbreviations and achieve high character savings. Second, users can utilize the LLM's power to write and abbreviate efficiently on SkipWriter's interface with diminished physical efforts. This is all I have for today's presentation, and thank you for listening. I'm happy to take any question.
We have time for one question.
Okay, thank you, Ze. This is Brian Wong from Adobe Research. Thanks for a great talk. I think it's a really elegant approach to deal with the problem. My question is about, I think typing or writing is quite often very personalized. And I wonder, have you thought about any approaches to, fine-tune your model, in order to really fit the prediction to individual preferences when they're writing using approaches like, like reinforcement learning with human feedback to make it a continual learning approach?
So that's a really good question. So the first thought on my mind is we're looking for end-to-end training in this situation, because right now we are using a recognize and decode approach, which means that the personal styles of the handwriting is handled by the recognizer, but the personal linguistic styles is not very well represented in the large language model. So if we can collect real human, abbreviated writing data and train a large language model end-to-end for it, that will be super helpful to incorporate both the personal handwriting styles and also the linguistic habits into the system. Also, as you suggested, reinforcement learning is also a good is a good approach to address it. Probably we can have some, if we can have on-device, right now it's remotely deployed. If we can have an on-device model for on-device inference or learning, it will be easier to incorporate adaptive learning on users' devices and therefore achieve what you said.
Awesome. Thank you so much.